Welcome back, everyone, to the deep dive. Today, we are diving into a really kind of a mind-bending area of physics, actually, topological insulators.
Yeah?
And we'll be drawing our insights from the essay Topologische Isolatoren, Revolution in Quantum Materialien by Jurgo Schnepper.
Right.
So to set the stage a little bit, topological insulators are these really fascinating materials that are attracting a ton of attention in theoretical physics and material science. So they have this kind of strange dual nature where they're insulators in the interior, but their surfaces are conductors.
Yeah.
And, you know, this kind of seemingly contradictory property is rooted in a really deep concept called topological order.
Yeah, it is a little bit, almost sounds like science fiction.
It does, yeah.
The fact that you can have a material that would prevent the flow of electricity through the bulk of it.
Yeah.
But then on the surface, it's like a perfect conductor.
Yeah.
So it's sort of like, you have a block of wood, but then painted on the outside is like a sheet of copper or something.
Yeah.
So very strange. And as you mentioned, this all arises from the topological order of their electronic band structure.
Yeah.
And that's something that is robust against external disturbances, so it makes it even more interesting.
Yeah, so let's unpack that a little bit. So our mission today is to really figure out what are topological insulators, how do they work, why are they important, and what is their potential impact on future technology?
Right.
So you mentioned band structure, and you mentioned this idea of topological order.
Yes.
Let's maybe dig into that a little bit, because I think, for folks who aren't necessarily physicists, these are pretty foreign concepts, but I think actually they're pretty intuitive once we start to kind of break them down.
Yeah, so maybe we can start with this idea of a band structure.
Yeah.
So in a solid material, you have atoms arranged in a very periodic way, right?
Right.
Like in a crystal lattice.
Right.
And these electrons in the atoms, they can hop from one atom to another, right? And as they do that, because of quantum mechanics, their energy levels are quantized, meaning that they can only exist at certain discrete energies.
Okay.
And the way those energy levels are arranged is what we call the band structure.
Okay.
So you can have a band of allowed energies and then a gap where no electrons are allowed and then another band and so on.
Mm-hmm.
Now, what makes topological insulators special is that while they also have a band gap, meaning that the bulk of the material is an insulator, the surface states, the electrons that live on the surface of the material, they're arranged in a very special way that's dictated by this topological order.
Okay.
So if you think of topology as basically the study of shapes and how you can deform shapes without cutting or gluing.
Right.
So for example, a donut and a coffee cup are topologically equivalent because you can deform one into the other without cutting or gluing.
Right.
But a sphere is different, right? Now, in the case of topological insulators, it's not the physical shape of the material, but rather the shape of the electronic band structure in what we call momentum space.
Okay.
And this shape is described by these topological invariants, which are numbers that capture the essence of the topology.
So it's almost like, if you think about the donut example, it's the number of holes that really defines its topology.
Exactly.
So is it like a similar concept when we're thinking about the topological invariant of a material?
Yeah, it's a very similar concept. Mm-hmm. So in the case of, say, the quantum Hall effect, which was one of the first examples of a topological phenomenon in condensed matter physics, the topological invariant is the Chern number, which is an integer.
Okay.
And it tells you basically how many times the electronic wave function wraps around in momentum space.
Okay.
And this Chern number is directly related to the Hall conductance, which is the ratio of the current flowing perpendicular to an applied electric field. And what's remarkable is that this conductance is quantized, meaning that it can only take on discrete values, which are multiples of a fundamental constant.
Wow.
And this quantization is a direct consequence of the topological nature of the system.
So this isn't just like a kind of a theoretical curiosity. This has actual, experimental measurable consequences, which is really fascinating.
Absolutely. And this was a huge discovery when it was found in the 1980s because it basically opened up this whole new field of topological phases of matter. And now we know that there are many different kinds of topological insulators and topological superconductors and all sorts of interesting materials that have these topologically protected properties.
So you mentioned the quantum Hall effect.
Yes.
Historically, how does that relate to the discovery of topological insulators?
Right. So the quantum Hall effect was really the first example of a topological phenomenon in condensed matter physics.
Right.
And it was discovered in the 1980s, and it really provided the theoretical foundation for understanding topological insulators.
Okay.
So in the early 2000s, two physicists, Kane and Mallet, they proposed that a similar phenomenon could occur in graphene, which is a two-dimensional sheet of carbon atoms, but without the need for a strong magnetic field.
Okay.
And they called this the quantum spin Hall effect.
Okay.
And the key ingredient here was something called spin-orbit coupling,
Okay.
which is an interaction between the electron's spin and its orbital motion. And this interaction, it effectively acts like a magnetic field that's internal to the material.
Okay.
And it can lead to the formation of these topologically protected edge states, even without an external magnetic field.
Wow.
And then a few years later, in 2007, the quantum spin Hall effect was experimentally observed in mercury telluride quantum wells, which was a huge breakthrough.
Yeah.
Because it confirmed that these topological insulators really do exist. And since then, many other materials have been found that exhibit topological insulating behavior, including bismuth telluride, antimony telluride, and many others.
So it really sounds like the discovery of the quantum Hall effect it opened the floodgates to this whole new field.
Exactly, yeah.
And then you mentioned spin-orbit coupling.
Yeah.
Which plays a really key role in this whole thing.
Absolutely.
So can you unpack that a little bit more for us? What is spin-orbit coupling, and why is it so important for topological insulators?
Yeah, so spin-orbit coupling, as I mentioned, it's this interaction between the electron spin and its orbital motion. Now, an electron, it has this intrinsic angular momentum called spin, which you can think of as like a tiny magnet.
Okay.
And it also has orbital angular momentum because it's moving around the nucleus of an atom.
Right, right.
And spin-orbit coupling, it couples these two angular momentum together. And this coupling, it can be quite strong in heavy elements like mercury or bismuth because the electrons are moving very fast and they experience a strong electric field from the nucleus. Now, in topological insulators, spin-orbit coupling is really the key ingredient that drives the formation of the topological surface states.
Okay.
Because it can lead to an inversion of the electronic bands.
Okay.
So normally in an insulator, you have the valence band, which is filled with electrons, and then you have the conduction band, which is empty.
Right.
But in a topological insulator, spin-orbit coupling can cause these bands to invert in certain regions of momentum space, meaning that the conduction band dips below the valence band.
Yep.
And this band inversion, it creates these special surface states that are protected by time reversal symmetry, which is another important concept.
Yeah, so let's dive into that a little bit, because I know you mentioned that before, time reversal symmetry.
Yeah.
So why is it so important in the context of topological insulators?
So time reversal symmetry is this fundamental symmetry in physics, which basically says that the laws of physics should be the same if you run time backwards.
Okay.
Right. So if you watch a movie of a ball bouncing, you can't tell whether the movie is being played forwards or backwards. Now, in the case of topological insulators, time reversal symmetry protects the surface states from backscattering.
Okay.
So imagine an electron moving along the surface of a topological insulator. Now, if it encounters an impurity or a defect, normally it would scatter off in a random direction.
Right, right.
But in a topological insulator, because of the spin momentum locking, the electron's spin is tied to its direction of motion.
Okay.
So in order to scatter backwards, the electron would also have to flip its spin. But this spin flip is forbidden by time reversal symmetry.
Okay.
So the electron can only move forward. That's why the surface states are so robust, because they're immune to this backscattering.
That's really fascinating. So it's almost like time reversal symmetry is kind of enforcing this kind of one-way street for the electrons.
Exactly, exactly.
It's amazing how these abstract concepts actually manifest in these really unique physical phenomena. So we've talked a lot about, the underlying physics of topological insulators.
Yeah.
Let's talk a little bit more about their properties.
Okay.
So Schneppett's essay highlights the really interesting combination of physical properties that make these materials so promising for applications.
Right.
For example, in addition to their unique electronic properties, topological insulators can also exhibit unusual thermal and optical properties.
Yeah, that's right.
So what can you tell us about, maybe to start, the electrical and thermal conductivity of topological insulators?
Yeah, so as we've discussed, the bulk of a topological insulator is an insulator. So it has very low electrical conductivity.
Okay.
But the surface states, They are excellent conductors. And this is because they are topologically protected from backscattering.
Right.
So the electrons can flow freely along the surface without being scattered by impurities or defects. And this leads to very high electrical conductivity on the surface.
Okay.
Now, in terms of thermal conductivity, it's a bit more complicated because the surface states also contribute to the transport of heat.
Okay.
But the bulk of the material is still an insulator.
Right.
So the overall thermal conductivity of a topological insulator is somewhere in between that of a metal and an insulator.
Okay. Okay.
And it depends on factors like the thickness of the material and the temperature.
So these materials have this sort of like this dual nature in a lot of ways.
That's right, yeah.
So Schneppat's essay really digs into the implications for spintronics and quantum computing.
Yeah.
So what are some of the ways that topological insulators might be useful in these areas?
Yeah. So in spintronics, the goal is to use the spin of the electron to carry information. And this has the potential to be much more energy efficient than traditional electronics.
Okay.
Which relies on the charge of the electron.
Right, right.
And topological insulators are ideal materials for spintronics because their surface states have this property called spin momentum locking.
Right.
Where the direction of the electron's spin is tied to its direction of motion.
Okay.
So you can imagine using a topological insulator to create a spin current where all the electrons are spinning in the same direction. And this can be used to build new kinds of transistors and memory devices that are much faster and more energy efficient.
So it's almost like you're not just using the electron to carry information, you're using its spin, which is like an additional degree of freedom.
Exactly.
That you can control.
Exactly.
That's fascinating.
Now, in quantum computing, topological insulators can be used to create these exotic particles called Majorana fermions, which are their own antiparticles.
Yeah, we've mentioned those a few times now.
Right.
What's so special about Majorana fermions?
So Majorana fermions, they have this really weird property, which is that they're their own antiparticles.
Okay.
So if you bring two Majorana fermions together, they annihilate each other. But if you separate them, they can still remember their previous state.
Okay.
And this non-local property makes them very interesting for quantum computing.
Okay.
Because you could use them to create qubits, which are the basic building blocks of a quantum computer that are topologically protected from decoherence.
Okay.
Which is one of the biggest challenges in building a quantum computer.
So it's almost like Majorana fermions have this sort of built-in redundancy.
Exactly, yeah.
Because they're kind of spread out in space.
Right.
And so even if one part of the system is perturbed, you know, the information is still encoded in this kind of this non-local way.
Yeah, that's a good way to think about it.
It's amazing.
Yeah.
So we've talked about a lot of really exciting possibilities. Schneppat's essay also points out that there are still theoretical and experimental challenges.
Right.
That need to be overcome before we can fully realize the potential of topological insulators.
Absolutely, yeah.
So what are some of those challenges?
So on the theoretical side, one of the big challenges is to develop more accurate models for describing the behavior of these materials. So many of the current models, they rely on approximations that might not be valid in all cases.
Okay.
Especially when you have strong interactions between the electrons.
Okay.
And another challenge is to better understand the role of disorder and defects, which can have a big impact on the properties of topological insulators.
Okay. Okay.
On the experimental side, one of the challenges is to synthesize materials with high purity and low defect densities. Because impurities and defects can scatter the surface states and reduce their conductivity.
Right, right.
And another challenge is to develop new experimental techniques for probing the properties of these materials, because many of the existing techniques are not sensitive enough to measure the surface states directly.
So it sounds like there's still a lot of work to be done, both on the theoretical side and the experimental side.
Yeah, absolutely.
But I guess that's what makes it exciting, right?
Oh, for sure, yeah. It's a very active area of research, and there's a lot of progress being made all the time. So it's a very exciting time to be working in this field.
So in conclusion, topological insulators represent a really remarkable convergence of fundamental physics and potential technological applications.
Yeah.
Schneppat's essay highlights the key role that abstract mathematical concepts like topology and symmetry play in giving rise to these really unusual materials.
Absolutely, yeah.
And the essay also underscores the importance of interdisciplinary research in advancing this field,
Right.
bringing together physicists, materials scientists, and engineers. As Schneppet kind of sums it up, topological insulators really are a revolution in quantum materials.
I agree, yeah.
So I think a final thought for our listeners.
Yeah.
Schneppet's essay focuses on the unique electronic properties of these materials and their potential impact on, electronics, spintronics, and quantum computing.
Right.
But it's worth considering how these materials might influence other areas of technology as well.
Yeah.
For example, their unusual optical properties could lead to new types of lasers and sensors, and their thermal properties could be exploited for energy harvesting and thermal management applications.
Absolutely, yeah.
So as we continue to explore and understand the world of topological insulators, I think we can expect even more unexpected and potentially revolutionary discoveries and applications in the years to come.
I agree, yeah. There's still so much we don't know about these materials, but that's what makes it so exciting.
Absolutely. Well, thank you so much for joining us today on The Deep Dive.
My pleasure.
And thanks again to Jorgo Schneppet for this fascinating essay on topological insulators.
Yes, great essay.
We'll catch you all next time.